In this lesson, we're going to talk about nuclear decay. So if you recall, previously we talked about stability in the nucleus. So elements 1 through 20, it's a 1-to-1 ratio of protons to neutrons. Elements 83 and above, they are always unstable. So neutrons have a lot to do with stability. They provide a strong force that holds the nucleus together. If the nucleus is unstable, it's going to decay, releasing high-speed particles and energy. And there are 4 types of decay that we're going to talk about: alpha, beta, positron, and gamma decay. If you recall in physics, we talked about a couple different laws of conservation. So these are going to come into play when we talk about nuclear decay. The first type of conservation that we're going to look at is the conservation of mass. So the reactant and product sides must equal the same total mass and atomic numbers. In terms of energy, mass and energy are convertible, and we're looking at Einstein's famous equation, E equals mc squared here. So products often have less mass than reactants, and that missing mass is going to appear as energy. And you'll see that when we do some examples here. All right, so the first type of decay that we're going to look at is alpha decay. So in alpha decay, a helium nucleus is going to be released. So you'll see that written one of 2 ways. So up here, I have it written out both ways. So if you look here, we have our mass number up top, and we have our protons down below. So we're going to break this into 2 different reactions, or 2 different steps. So on the top, when we're looking at mass, we don't know what's on the left side of our reaction, our reactant side. This arrow is kind of like an equal, so I'll just put an equal there. It separates the 2 sides. So we have 222 plus 4 for our mass. And then for the number of protons, we have 86 plus 2. All right, so 222 plus 4 is 226. And then 86 plus 2 is 88. So if we go and look up 88 on the periodic table, that is radium, Ra. And when we go to write out this in the correct notation here, it's going to be 88 on the bottom, the number of protons, and then 226 are going to go up top. Okay, so this would fill in on our blank right here. Just didn't have enough space. All right, let's look at the next one. Here's another example. So same thing, we can break this into 2 steps. So on the reactant side, we have 222 equals blank plus 4. And then we have 86 equals blank plus 2. So blank plus 4 equals 222. Well, that's going to be 218. And then 2 plus blank equals 86. That's going to be 84. Again, we go to our periodic table and we look this up. This is going to be polonium, PO. 84 is going to go down here. And then 218 will go up here. All right, in this example, it says francium 220 undergoes alpha decay. So if we go to the periodic table and we look up francium, francium is Fr. Its mass number is going to be 220. So remember, anytime it's written out like this, that dash and the number, that number is the mass number. Francium on the periodic table is number 87. If it's undergoing alpha decay, we're always going to have that helium nucleus. And then blank. Well, again, we have 87 on the reactant side. So 2 plus what gives us 87? Well, that's going to be 85. Same thing on the top. What plus 4 is 220? That's 216. And if we look up 85 on the periodic table, that's astatine. All right, next we're going to look at beta decay. So in beta decay, the neutron decays into a proton and an electron is released. So if you notice here, we have a negative where the proton would be. So for this one here, looking at the bottom, we have 85 plus a -1. So for this one here, we are going to do a little bit of subtraction. Remember, when you add a negative, it's the same as subtracting. So this will be 84 down here. Okay, 218 plus 0 is still 218. If we look up 84 on the periodic table, it's polonium, PO. Okay, here's another example of beta decay. So be careful with this negative. A lot of people, when they see the negative, they want to like do weird things. They want to like add it to the other side. No, don't do that. Okay, so when we do this, we have, I'm going to write this out just so you can see what's happening. So we have 81 equal to blank plus a negative is the same thing as subtracting 1. So what minus 1 is 81? Well, that's going to be 82. So 82 goes down below here, and then we'll have 210 up above. 82 on the periodic table is lead, Pb. Okay, potassium 42 undergoes beta decay. So again, this is written out. Potassium is one of those goofy ones on the periodic table. Instead of starting with the letter P, this one actually is, the symbol is K. So K is potassium. Potassium is 19 on the periodic table. Our mass number is going to be 42. Okay, since it's beta decay, it's going to be -1. You can write it out with an E, or you might see it like this, written out as a B, B with a little tail. Tail's probably longer than it should be. All right, and then plus blank. Okay, so we have 19 on the left side. So what minus 1 is 19? Well, that's going to be 20. And then what plus 0 is 42? Well, that's going to be 42. 20 on the periodic table is calcium. So again, be careful with those negatives. Okay, many nuclei go through a series of reactions called decay series before they reach stable nuclei. Uranium-238 goes through a series of alpha and beta decay before becoming stable. So in 1977, the Voyager spacecraft was launched. It's that spacecraft that we launched to go explore the solar system. So, we've got our sun here. All right. So when things are really close, so like, here's Earth. So when things are really close to the sun, we can use solar power to power spacecrafts. They have those big solar panels. But, Pluto's way out here. Voyager's way past that. So when we get past Pluto, there's not enough sunlight to generate electricity. So rather than powering, it's not Pluto, it's supposed to be Pluto, to generate electricity, so we are actually using nuclear decay. So there's a radioactive isotope, a big chunk of it, that's powering the Voyager spacecraft. So this nuclear decay, this series of nuclear decays that's occurring on the Voyager spacecraft is actually what's generating the electricity. Fun fact. So here's what this looks like. So we start with uranium-238, and it undergoes a series of decays. Every time there's a decay, there's a little bit of energy that's released. So it's a series of alpha and beta decays. And eventually we reach something that's a lot more stable. So the Voyager spacecraft is going to continue to operate like it. Less and less electricity is generated each year. They're predicting 2025 is when the electricity, when there won't be enough left of that isotope to continue to power the spacecraft. But think about it, that's a long time for this to generate electricity. It's a much better power source than solar power. All right, so positron decay is the opposite of beta decay. So it's the anti-electron. So identical in mass, but opposite in charge to an electron. So this is a little bit easier because we don't have to worry about a negative here. So 9 plus 1 is 10. 19 plus 0 is 19. If you look up 10 on the periodic table, 10 is neon, Ne. Here's another example. So what plus 1 is 26? That's going to be 25. 0 plus 53 is 53. So here we look up 25, that's manganese, Mn. Here's another one written out. Manganese 23 undergoes positron decay. So we've got manganese, Mn. 23 is the mass number. And if you look this up on the periodic table, it's number 12. It's undergoing positron decay. It's going to be plus 1. B with the little tail there. Remember the difference between beta decay and positron decay. Positron is going to be plus 1. Beta decay will be minus 1. Okay, plus blank. So here, 11 plus 1 is going to give us 12. And then, of course, 23 plus 0 is going to give us 23. And this is going to be sodium, Na, which is number 11 on the periodic table. All right, the last type of decay that we're going to talk about is gamma rays. Gamma rays are bad news. Gamma rays are very harmful to our body. And all these are is just pure energy. There's no mass here. So if you look, it's just 0 mass, 0 protons. And then we have that weird squiggly line. Okay, so gamma rays are high frequency electromagnetic radiation that's released when a nucleus stabilizes. So these are really easy to spot because notice the proton, oops, that's not what I wanted to do. I was trying to highlight here. The protons and the protons are the same. So the reactants and the products are the same. And then the mass is the same on both sides. So gamma rays are easy to spot because it's just 0, 0. The last thing we're going to talk about is transmutation. So transmutation is where we change one element into another by bombarding the nucleus with another particle. So this is alpha bombardment. So we have a helium nucleus. We want to make sure the reactant side and the product side are balanced. But before we do, I made a mistake here on my notes. This should be 1, 0, not 0, 1. Remember, neutrons have mass, but they don't have any protons. Okay, so what we're going to do is we're going to add up the left side's protons and the right side's protons. So we've got 4 plus 2 is going to be equal to blank plus 0. 4 plus 2 is 6. What plus 0 is 6? Well, that's going to be 6. Let's do the same thing with the masses. 9 plus 4 is going to be equal to blank plus 1. So 9 plus 4 is 13. And then we have, let's see here, what plus 1 is 13? Well, that's going to be 12. 6 on the periodic table is carbon. Okay. Here's another example. Plutonium-230 undergoes alpha bombardment to produce a new atom and 1 neutron. Okay, so plutonium-230, Pu, 230. Plutonium is number 94 on the periodic table. Okay, it's undergoing alpha bombardment. So since it's alpha bombardment, it's going to be 4, 2 helium, producing a new atom plus a neutron. So a neutron is 1, 0, and then neutron. Okay, so we've got 94 plus 2, that's 96. And then we have 230 plus 4, that's 234. On the other side, we have a 1. So 234 minus 1 is 2 33. Okay. And then if we look this up, this is going to be Cm. It's number 96 on the periodic table. Okay, here's another example. This is proton bombardment. So this, we haven't seen this yet, but this is a proton. Again, we just want to make sure that both sides are balanced. So 3 plus 1, and again, there's a mistake here. This should be 1, 0. 3 plus 1 is 4. And then we have 7 plus 1, that's 8. 8 minus 1 is 7. So if we look this up, number 4 is beryllium, Be. Okay, so just to review, these are all the symbols that we talked about. So for our exam, when we go to take our exam here, you do need to know these. So I highly recommend flashcards. Okay, flashcards are your friend for sure. Let me just kind of write that out. Flash cards are your friend. All right, good luck and have fun.